My name is Anna Steffi, and I am Group 19.
I'm Zach Barnett, and I'm part of Group 19.
I'm Alana Jadwalis, and I'm also in Group 19.
I'm Zolingjia in Group 19.
And this is a recording for recitation 8. And this is our shared document. We have a lot of collaboration, a lot of work. And this, we're doing the multi-particle energy principle. And we're standing on the model comet's surface, use the energy principle to determine the minimum speed at which a ball of mass m that you throw straight up would have to leave your hand in order to not fall back to the comet's surface. So I just started personally with like the velocity of like escape. I think it was in our notes. Like it was basically an equation. But I also just derived it from the principle. What did anyone else get?
Yeah, for the equation for velocity, we got the same exact thing pretty much. I mean, we wrote it a little bit differently. I think didn't have quite the same exact path to get there, but we got the same thing.
Yeah, I also got the same thing because the final kinetic and potential energy are basically zero.
Yeah.
Yeah.
Mm-hmm. I think that's what connected most of us together, or all of us together easily. I think all of us assumed that those two were zero and just solved. So for part 2 on this comment, it would be possible to play catch with yourself in the sense that you can throw the ball horizontally so it moves along a circular orbit and you can turn around and catch it as it comes around to your location again. Use the momentum principle to determine the speed at which the ball must leave your hand for this to happen. How long must you wait to catch the ball after throwing it?
I think we all had a pretty similar path here as well.
Yeah, I think we have the same formula.
Mm-hmm. Yeah, I think we all start with some quantization of force to get to speed. And then for time, as it says, these two are really closely linked. Just distance over velocity average. So we could just use that for the time. Yep, same thing. Okay, part 3, the mass of the comet. And then we have the radius and horizontal speed. Did anyone have any problems with this one?
I got the same speed, like about 1 like meters per second, but the t, like the time, is a little bit different. I didn't put the images here, but probably I'd make some errors during my calculation.
Let's see. And I found this one pretty hard. Yeah, it looks really similar. So problem 2, A pendulum consists of a thin, rigid, massless rod of length L and a bob of mass M. From point A, the bob is projected downward at a speed of VA, such that the bob reaches point D and stops there momentarily. The velocity of D is 0. Ignore air resistance. If the potential energy at B is 0, and problem 2, problem 1, we have momentum is mg, mgl, yeah.
I didn't quite finish I just find that like for part 2 of problem 2.
B,
Oh yeah, I did the time wrong in part 3.
yeah. I thought the energy at A would be, the potential energy was like really simple because it's just this equation that we have always used. And yeah, I defined my system as such, so I could have no work and such. Yeah. Yeah, and whenever I'm going to be asked for velocity, I always assume that there has to be some kinetic energy component factor to relate to velocity so I can find it. I always try to just start with delta E equals W. And that's how I got that answer. At which point does the bob have maximum speed, and what is the maximum speed? What was people's answer for number 3 on problem 2?
Point B was well the point versus maximum speed. And
Yeah,
then I had radical for GL. That's mine.
Yeah, same answer.
Awesome. Okay. I think that's the list of the last one. For maximum tension, I got 5 mg, and that is the same with Gia's work as well. Did anyone else get anything different?
I did. I think I may have done something wrong. I can't exactly point out to you what is wrong, but I did do it differently. I got a different answer. Yeah. So I did the acceleration is equal to v squared over L route for circular motion, and that's what I did. And I simplified that down. Got acceleration is equal to 4g. Plug that into everything. I got a difference.
I'm thinking actually maybe the first mg would be negative, like because it's pointing downward, but it's just me guessing.
That's an idea. F. Alana, did you get 5 mg too?
I just left it without substituting back in the velocity, so yeah,
Okay.
I didn't realize to do that.
Okay. Is everyone okay with what we've had?
I did the time wrong on part 3. So Gia's time was correct.
On part 3 of problem.
Oh, way far back.
Oh, problem 1.
Yeah, I think.
Okay.
Yeah. I forgot to multiply it by mass, I think.
Well, for part 3, what is the speed then? It asks for speed starting from the fundamental principle. Explain how you determined it. The figure on the next page is a graph of the comet ball system, gravitational potential energy in joules as a function of their separation kilometers. Plot the line on the graph that represents the ball's elliptical orbit. See figure 6.43 on page 256 of the textbook for examples. Also plot the point representing the circular orbit you analyzed in part 2. Yeah, we have to plot on this, I think. I
Yeah.
just realized that. I did not. But we didn't have to find time.
Oh, I meant for earlier in part 3. Because part 3 is like 2 parts.
I thought you meant the extra one that I'd seen earlier that I was like, I wonder why. We got same. Did I do it wrong too? Where are you talking about?
Scroll down a little bit.
Mhm.
That right there.
This.
Yeah, that is wrong.
Yeah. Okay.
Just like crop it out. Or I can just paste the right one.
Just okay. I think we have to plot something now. So hold on. Plot the line on the graph that represents the ball's elliptical orbit. The point representing the circular. So we have to do part 3 and part 2. Oh, okay. So in part 2, whenever we throw the ball, it is like basically like just skimming the surface. And this is distance from, I'm assuming when we throw it, from what I've seen, like from like other example problems, it like they show it and they describe it as like being very like close. And that's why we can use R, because it's like just so close to like the actual radius. If it was super far away, like if we threw it like 5 feet above a 7-foot radius, like that would be a problem. Ball system. So if the ball is like always really close to the surface, I don't know how that would affect how this looks.
Well, so they want 2 points, or like a line and a dot, and the x-axis is the radius. So do you literally just put like the initial radius to the like final radius, the largest one?
The initial radius to the final radius. For part 3 or part 2?
The one with the plotting on the graph.
Yeah, so whenever it asks for plots, it wants us to plot the circular orbit we analyzed in part 2. So that's one thing we have to do. And we have to plot a line that represents the orbit that we just calculated. So we need to, it says plot the line on the graph and plot the point. So we need one line and then a point, like you said.
Yeah, so I think the line would be 1.5 to 6.4. Because it's just the distance.
Okay. Can somebody with like a pen do that? Right on the document? We can do that after we close off the Zoom meeting. As long as we agree on what we would like drawn beforehand. Does anyone have a textbook to look at this?
I
So-
wish I could say I did. I don't think
Page
I do.
253. Oh wait, how do we even get to the textbook?
Oh, it's on, is it on Wiley? I don't remember.
Yeah.
I've checked the online textbook, but I mean I don't quite understand the image is provided there. I would make screenshot and post in the group link.
Thank you.
Alright, yay. Well, I think I agree. I think that we should be drawing a line from 1.5 to 6.4.
I've posted the image in a group me.
Thank you. Oh yeah, that is helpful. Okay, so yeah, I think we gotta have like B will be 1.5 to 6.4, and then we need a dot. Where like C is. How do we find C?
Do you remember where in our notes it had those graphs? I think it was one of like the lecture quiz questions too, where it said what A and B and C were. I don't know if that would help, but
I do not. I'm making some calculations.
Tech said he's going to leave for work. Like,
Okay, well, we can stop it here and,
yeah, we should probably stop it and just
okay,
figure out the news. Yeah.
Sorry, guys. It's just.
Okay.
I'm
I'll write
happy
on
that
the-
that is, yeah.
okay.